Hello, this is Professor Elliott, and in this lesson today, we will look at BJT switching circuits. Okay, so review of the collector curve. Again, transistors have two primary applications. One is as an amplifier, and the other is essentially an on-off switch, which is the application we are looking at today. Recall from the earlier discussion on the introduction to the BJT, the transistor can be biased in the active region, and in that case, that's where we have the high current gain, roughly in the range of 100 to 300, but don't be dogmatic on those numbers, but that's general range. That's going to be up in here. For an amplifier, you always want to be biased up in this range. There are exceptions, of course, but as a general rule, that's where you want it. You can also bias a switch here in the active range, or you can bias a switch in the saturation region. It just depends on the application. Okay, so once again, if you consider the DC low line, which we've looked at previously, then the upper and lower ends of that low line are called saturation, IC sat, and the lower end is cutoff, or VCE off. At cutoff, it's assumed that the transistor is behaving similar to an open switch. Not exactly true. There is leakage current. So therefore, we could say then that when in cutoff, the collector to emitter voltage is approximately equal to VCC. And at saturation, it's behaving as a closed switch. Again, that's never quite exactly true due to the saturation voltage. But in that case, the assumption is that VCE is equal to 0 volts, and then you go ahead and calculate your saturated current. Okay, so this is just the same thing. Just gives an example. Okay, if you have a 12 volt supply, right, an open switch, you have the full 12 volts across it. A saturated transistor, you have a little bit less because you have the saturation voltage collector to emitter that you can never make 0. So one of my cats is very lonely right now. Come on, Chip. Chip, come here. Come on. Want to help? Come on, Chip. Come on. Come on. The class wants to see you. Come on. And then with a closed switch, obviously, if the switch is in good condition, the voltage across it will be 0. And this is typically the saturation voltage. It varies on the current and how deeply it's saturated, but anyway, have a look at that. It's very important stuff. Okay, so NPN switch scenario number 1. I am by no means going over every possible circuit configuration. I'm just giving you a bunch of them to get you used to how the transistor operates. So this is meant to be detailed, but no means absolutely comprehensive. Okay, so in this case, if the switch is open, obviously there's no base current. If there's no base current, there's no collector current. If there's no collector current, then the LED is actually going to be off. And then of course, when we close the switch, then we have base current. we have collector current because of the current gain, and the LED comes on. Okay, so for all these circuits, please make a copy of it, because I'm not coming back and forth to refer to the circuit. I'm just going to continue to solve each one right after another, with my comments, of course. But you absolutely must have the circuit diagram in front of you, so pause the presentation now to make a copy of that. Okay, so anyway, so let's go ahead and solve it. And the steps that you take, it depends on the actual circuit. Okay, just kind of look what you got and then proceed accordingly. Okay, base current is equal to voltage VBB minus VBE (86 microamps). Okay, collector current, base current multiplied by the current gain, and that was times, okay, 65. 5.59. Collector resistor voltage, collector emitter voltage. Again, must have the diagram in front of you, otherwise this will make no sense at all. Okay, depending on the color of the LED and how much current is flowing through it, roughly an LED has 2 volts across it. Could be as low as 1.5, maybe up to 2.5. Anyway, you can get that off the data sheet for the LED. Okay, and yeah. So anyway, so that's it. There's enough current there to light the LED. You know, somewhere you want 5 to 10 milliamps, rule of thumb, for an LED to get reasonable brightness. Look at the data sheet. Most of them can handle significantly more current. Again, it's application dependent. So, but anyway, that's number 1. Hi, Katie. Okay, NPN switch number 2. Okay, this one's a little bit different because I intentionally put the LED in the emitter side, which means then we're going to have to reflect or move that that resistance R2 to the base side. Otherwise, there's no way to solve this unless we already know VR2, which of course we don't. So VN is just a 2-pole switch. If it's in the 0 volt position, there's no base current, and no base current, no collector current, the LED is off. If it's in the up position, we have 12 volts at VN, and the LED is going to come on. So again, take a picture, sketch it down, do whatever you need to do, and then when you're ready, please follow right across R1. Agree with me on solving this. Okay, so we can write the equation that VR1, okay, equals, so this is the voltage, okay, equals VN minus VBE, just use 0.7 unless I tell you otherwise, minus the LED voltage, which we know, and minus VR2. Okay, so if we knew all those values, we could solve for VR1, but because I didn't give it to us, but we don't know voltage VR2, so we have to use a little different technique. Okay, so reflect move R2 to the base side. So that gives us sort of an equivalent. You're not really doing this. Okay, you're just doing it in your head. Okay, and this is just going to go up to there. So this is going to be R1, and this is going to be beta DC R2. So on the collector side, the current is beta times larger than on the base side. So therefore, or you can look at it on the base side, the current is beta times less than the collector side. So therefore, we need beta times more resistance. So we have high resistance, low current on the base, low resistance, high current, relatively speaking, of course, on the collector emitter. So that's the technique. Okay, so beta DC R2 equals 160 times the 1K equals 160 K ohms. Okay, so now then we can say then base current IB equals VN minus VBE. Okay, that's the base to emitter loop. Okay, please look at the diagram. R1 plus $12 and this is 149.7 microamps. Okay, the collector current, which we said before, is essentially equal to the emitter current equals the base current times the current gain okay, so almost 8 milliamps. Okay, VR2 is 7.96 volts. And step 5, VCE, look at the diagram. Okay, 2 volts across the collector to emitter. Okay, PNP switch. Okay, you know what's a PNP. Again, the switch is open, so there's no current flowing base or emitter through the base. So there's no base current, so there's no collector current, so the light is off. When you close that switch, okay, then we have a current path. Okay, just look like that with the switch closed down to the down to the common ground and back to the battery. Notice that the power supply is now called VEE because that's feeding power to the emitter, and the other ones it was VCC because it's feeding power to the collector. Okay, small but critical in difference. Okay, so let's go ahead and decay. So we have to mentally then flip that to there. Not a, then solve this one. Make sure you've recorded the drawing. Okay, so first step, similar to what we did in the last problem. Okay, we have to remove, reflect or mentally, visually move RE. Okay, to the base. So from the base side, RE looks like 100, of course, just in our using our visualization. Okay, so again, just a little memory aid sort of diagram. And then we have our LED there, right? And this is going to be RB. Okay. And yeah, so this is our 170K. This is 15K, which means we effectively have 185 K ohms total. Okay, so let's just call this, just for the sake of easy reference, Vx. This Vx is the theoretical voltage across RB, which you can measure, beta DC RE, which is conceptual, right? So that's where that. Okay, voltage Vx equals V E minus okay, so that falls. Okay, 9.6 volts. And this is step 2, I think. I screw this up. 3 base current equals Vx (9 microamps). Emitter current equals base current (8.8 milliamps). Okay. 6 equals minus VRE equals 12 minus. Okay. All right, so we're still biased in the active area with that much, that high of a VCE. All right, oops, sorry. Let's continue on. Okay, some homework practice questions. Okay, which I'm going to solve for you. Again, draw this, sketch this down, and then let's solve it. Okay, step 1. Again, you just have to learn. Don't memorize the formulas. Look at the circuit. What do you got? And then proceed on that basis. Okay. Okay. I don't memorize anything. I've just found ways many years ago to visualize the circuit, so I can in my head see what's going on, and solve it from there. And it's absolutely wonderful because you don't have to memorize a thing. So anyway, that's the point I hope you get to. If you have to memorize, then go ahead. But as I said 100 times over the years, or probably more than that, anything you try to memorize, as time goes on, tends to fade. If you actually are able to genuinely learn it, then that tends to stay with you much longer. So anyway, totally up to you. Okay, so we're just proceeding logically through here, and I would encourage you to record these values directly onto the diagram to reinforce, where their real values, where they actually fall. Okay. Okay. Again, it's biased up in the active area. Yep. All right. Okay. Homework problem number 2. This one, obviously, if you want the LED on, you got to close the switch, and we're going to have to, like we did for a couple other times, move that emitter resistor to the base side. Otherwise, we are dead in the water. So, okay. Reflect. Resistor RE. To the base. Okay, equals 100 equals 100 k ohms. All right, put all those values in. You get 48. Okay. All right, and number 3. Emitter current, IE, 48. 4.87. Okay. Okay, again, because it's greater than 0.7, that's biased. I guess just interchange steps 4 and 5. But anyway, there it is there. Active area and VRE would have been IE times RE, which is 4.87. Which, yeah, I guess so. We should have, anyway, we should, okay, so, okay, I'm hoping once you get onto it, it's not too difficult. It really isn't. You just need to spend some time working on it. And that's all it takes, really. Okay, number 3. Okay, again, right, close the switch, and then in that case, you tie the left side of RB to ground, allows current to flow from the emitter to the base and get base current, and through the beta DC, you get the high collector current, and the LED comes on. Whoops. Okay. All right, step 1. Okay. Move RE to base. Side. So okay, you should be getting used to that technique by now, I hope. All right. Okay, so I guess this is step 3. Okay. Equals 52 times, I think that was 100. And 170, yeah. Sorry, I was looking at the wrong drawing. 8.91 milliamps. Yeah, that looks all right. Okay, for the voltage across the emitter resistor, equals 8 okay, just Ohm's law. VCE equals VEE minus 1.49. Again, bias in the up in the active area. As we're just turning on a light, then there's no need to totally saturate the transistor. Why not have the high current gain? But there are applications, as if you're feeding into a controller or something, then you probably want to highly saturate the transistor. But again, as in always, it depends on the application. This is our last problem. Okay, hold the push button down to make the light come on. Okay, notice that's required to, this is a PNP transistor, to correctly bias the transistor. And the question is that if we have 6 volts here and we have 14 volts there, okay, the beta is 65, then what are the values of base resistance and collector resistance? That's what we want to solve. Okay. The other things that's missing is what is our desired collector current. So let's use 10 milliamps for that. Okay. And let's let our VCE be negative 1.2. So what do we have to do then to solve for RB and RC to make that all true? Okay, so take that down. The beta, we're going for a lower beta because we're getting down near the saturation region, so we expect the beta DC to drop. Right, so let's just give you, no, I didn't give you the LED voltage here. I want that to be 2 volts. Go ahead with your circuit in front of you and solve it. Okay, so equals negative. Okay. Negative 1 point. That is 10 points. Sorry, negative 10.8 volts. Okay, as I might have said in a previous video, okay, I don't really bother with the negative voltages. I just throw the negative in at the end, because if the power supply is negative, obviously the voltage is going to be negative. Okay, so that way I don't tend to confuse myself so easily. Okay, no, okay, so sorry, that's where that I didn't give it to you. So that's what we wanted. Okay, 2 RC equals VRC divided by IC. Okay, I'll just throw the negative in here for form. There's really no need to put it there because the current will be exactly the same. But anyway, so you get 1.1K. All right. Number 3. The base current is equal to the collector current divided by the beta DC. Okay. Just don't bother putting negative values on the base current. It doesn't mean anything. On the voltages, obviously yes, but on the current, just leave it as an absolute number. Okay. 4 RB minus 0.7 volts, which is your VBE. Again, I'm just leaving the negative off just to make my life easier. 285. Okay, if you wanted to be technical about that, you'd be minus 6 plus 0.7. But I just choose to leave it off. Okay. This is 18.55K. And you just go the nearest higher, just get the nearest standard resistor size, which I'm not sure if it's 18 or 20 or 19. I'd have to look, but anyway, that's all for today. Thanks for spending some time with me, and I wish you all a great day. Thanks. Bye-bye.